And I want to ask if everyone has been able to view the video from Monday.
Yeah.
Good. That's real important because what we're going to do tonight hinges on the idea that you did watch that video. I'll sort of drop some redundancies to catch up, anybody who maybe didn't watch that, but hopefully you spent class time on Monday watching that pre-recorded video where we started talking about quantified statements. And just to review, there are two quantifiers. There's the universal quantifier for all, and there's the existential quantifier, there exists. And the idea is when we have a statement that's a for all statement, then we understand that whatever the predicate is or the property has to hold for all elements in the domain. And when there's an existential statement that's true, we're saying there exists at least one object in the domain for which the property holds. And that discussion involved mostly informal statements in ordinary English. So when we got to the point where we were going to be negating quantified statements, we learned that when we negate a universal statement, we get a there exists statement. So if it's not true for all elements X in domain D, that X has some property, say P, then there exists at least one X in that domain that does not have that property P. So when we negate a universal statement, we get an existential statement. Similarly, when we negate an existential statement, we get a universal statement. So if it's not true that there exists at least one X in domain D, such that P of X, X has property P, then for all X in that domain D, that property fails. So these negations make sense, and we're going to just continue along those lines tonight. And we're going to look at multiply-quantified statements. So this looks like multiply-quantified statements. Let me pin this. It looks like multiply-quantified, but we read this multiply-quantified. So statements with more than one quantifier, right? So we're going to also learn to negate multiply-quantified statements, and then we're going to play games with Tarski's world. Now, I did send out an announcement. I asked everybody to please download the Tarski worksheet 1 that's in the class 7 notes, the class notes for today. They're already up. I'm going to have that Tarski's worksheet to put under the camera, so if you didn't have a chance to download it, I'll be trying to put that where we can see it while we discuss it as much as possible. By the way, when I printed it out, the gray didn't really print as gray. So these little stripes, that means gray. And then there's black and there's white objects. So, and then there's some instructions for preparation for day 8 class on the class notes. But let's go ahead and get started with these multiply-quantified statements, unless anybody has a question. Does anybody have a question? We good? Okay, so here we go. There are kind of 4 ways to mix and match these quantifiers, okay? We're going to just play games with statements that have 2 quantifiers, all right? So it could be that it's something like this, for all. In other words, for all X in some domain D, and for all Y in some domain G. They might be the same, but they don't have to be the same set. Property P of X, Y holds. So P of X, Y is just some statement that involves X and Y. And we'll look at lots of examples tonight so that you can get used to this idea of not just P of X, but P of X and Y. So for all. And this means, exactly what we think it means. It means for every X in this set D and for every single Y in this set G, this property is going to hold some relative property. Then there's the case where it might be there exists. So they would look like this. There exists an X in D, and there exists a Y in G, such that property P of X, Y holds. And that means exactly what you think it should mean. It means there's at least one X in set D and at least one element Y in set G, such that this predicate P of X, Y holds for that X and Y, okay? But there are two other ways to mix and match two quantifiers. It could be like this. For all X in D, there exists a Y in G such that property P of X, Y holds. And we're going to have to talk about this because there's something to this. We'll need to try to understand that. And the other one, of course, is there exists an X in D such that for all Y in G, P of X, Y holds. And these two are the ones that aren't quite as natural in terms of our understanding them intuitively. And these are the ones that we're going to really try to focus in on tonight to make sure everybody understands that there's a big difference between for all there exists and there exists for all. And just to make a little note, it's perfectly possible for the domains to be the same. So D equals G, these two domains for X and Y respectively, D equaling G is possible. They could be the same set. And lots of times they're the same set, but it's not necessary. They might be different sets, and we'll see examples of that tonight too. So let's start with the first kind of version of or flavor of multiply quantified statement. We'll just call it Roman numeral 1 for all X in D and for all Y in G. Some property P of X, Y holds. Some predicate P of X, Y is true. Okay, this means just exactly what you think it means. So the way that we interpret this, there's nothing surprising. It's true if the predicate P of X, Y holds for every X in the set D and every Y in G. So let's just go ahead and look at an example right off the bat so that we can understand what the heck this is saying. All right, so this is saying, in this example, let's say for all X in the reals, let's just do a number type example, and for all Y in the reals, so here D and G are the same set. The predicate is a compound predicate X is greater than Y, or X is equal to Y, or X is less than Y. So this says no matter what real numbers X and Y you look at, this predicate is true. And in fact, of course, that is true. This, in fact, is called the trichotomy principle. If we take any two real numbers, they're comparable. One will be less than the other, or they'll be the same number. They'll be equal. So this is actually called the trichotomy principle, just FYI. I'm not going to test you on that, but it's something that's worth knowing. That, you know, there's a name for this idea that any two real numbers are comparable with the less than symbol or equals to. All right, now let's look at an example that's kind of just more silly, not a number example, but just a kind of little silly example. I'll let D equal the set of all dogs, and let's let G equal the set of all cats. And we could make up an example using that D and that G. So here D obviously is not equal to G. For all X in D and for all Y in G, X loves Y. So we're saying every dog loves every cat, which I think we all know that certainly is false. So it's just kind of a silly little example. You know, so how would we verify that it's false? Well, some dogs, you know, hate cats. In fact, that's more than we even need to say. It's enough that a dog hates one cat, you know, and we know that's true. In fact, in the WebAssign, there are kind of some fun, intuitive examples that you'll be working through. where I think there's one where there's some students and they all went to the cafeteria and they picked drinks and they picked salads, maybe they picked main courses, they picked desserts. And then you get to answer questions like for all students and for all desserts, the student had that dessert, which turns out not to be true because some kids had one dessert and some had another. So my point is we can have mathy examples where we really do have to think about properties of real numbers, and we'll see plenty of those tonight. Or we can have kind of just fun, intuitive examples, and you'll see both of these kinds of examples in the homework on WebAssign, which is already posted. And remember, if you wonder when things are due, there are, well, several places that you can see due dates. The reading page is your one-stop shop. Man, if you're not checking out the reading page on a regular basis, I encourage you to do that, because when everything is due is up there. Information about, when tests are going to be, information about videos that are available or documents that are available in the good stuff folder. That's all there for you to see kind of in one fell swoop in the reading page. Also, a student last year asked me to please use the Blackboard calendar. So I do. In the Blackboard calendar, everything that's due appears there. So you can look at the calendar and there's a little dot on the days when something is due. So you can do that. And of course, in WebAssign, you can always see what's due when. All right, so that's the for all. Super easy, super intuitive. And now let's move on to the there exists type of statement. Also, it's going to be very intuitive, super easy to understand because our usage is just like ordinary English. We like it when that happens. So here's the form for there exists an X in D and there exists a Y in G such that P of X, Y. By the way, we use the phrase such that after the existence quantifier. It's perfectly natural when we read this to say there exists an X in D and there exists a Y in G such that this property holds. So you'll hear that. It doesn't make sense to say such that after a for all phrase, but it does make sense to say such that after a there exists phrase, just FYI, in case you're wondering about that. So how do we interpret this? Well, exactly how you think we should. There exists some X in D, that means at least one, and some Y in G, such that P of X, Y, that's a property, is true. Just what you think it should. Let's look at some examples just to drive this idea home. Let's do a mathy one. There exists an X in the reals, and there exists a Y in Z. Remember, Z is the integers, right? 0, 1, -1, 2, -2, 3, -3, such that X is greater than Y. So this says there does exist a real number and an integer where the real number is bigger than the integer. And I think we all know that's true. So I'm just going to use an example to introduce an irrational number. We could just let X equal pi. You see, we just have to find one example. So we can just pick an X and a Y that work. So if we let X equal pi and Y equal 3, clearly pi is greater than 3, right? I picked a real number and I picked an integer. In fact, integers are real numbers. I could have picked X equal 4, but I kind of wanted to make the point that the set of real numbers is bigger than the set of integers. Any questions? Let's go back to our silly little example with dogs and cats. There exists an X in D, and there exists a Y in G, such that X loves Y. So here D is dogs and G is cats. So for this to be true, there just has to be one dog in the world and one cat in the world where the dog loves the cat. And I can tell you right now, this is true. I have a dog and a cat, and my dog loves my cat. So I'm just going to say my justification is Dr. G has a dog and a cat where the dog loves the cat. In fact, sometimes you might hear my cat meowing or my dog sitting here snoring or dreaming while I'm teaching. So just a couple of simple examples, one with numbers and one with dogs and cats. Now let's get to the meat of it. Let's get to the stuff that's a little more interesting. What if we have a for all followed by a there exists? Here we go. The form is for all x in D. Oops, I want to make D here. Yeah, my dog's snoring right now. Could be heard his name and he's starting to snore. For all x in D, there exists a y in G such that P of x, y. Okay. Now, what we learned on Monday is that there are lots of different phrases that can be used when we are talking about a universally quantified object. We can say every, we can say for all, but we can also say each. And that's the way I think that you would be best served when you're trying to interpret this statement. So I'm just going to put this here as a pointer that the best way to read a for all there exists is to read it for each x in D. There exists a y in G such that P of x, y is true. Now, why would I ask you to do that? Because the interpretation of for all there exists goes like this. Take a look at each x in D kind of one at a time. Okay, so we're looking at them one at a time. That's why I'm saying for each. So when you're looking at an x in D, we then have to find a corresponding y in G that works for that x to make P of x, y true. Different x's in D could have different y's from one another that work. So let's write that down. The interpretation is given any particular x in D, there is some y, at least one. It suffices to find one in G that makes P of x, y true. So the thing to understand is this, folks. Different x's, different values of x can partner. I think about x having a partner y. Different x can partner with a y that is not the same as for other x. In fact, each x could have its own y that no other x would be able to work with. Okay, so let me look, let's look at an example here so this can become clear. Example 5. For all x in the reals, there exists a y in the reals such that x plus y equals 0. Let's look at our intuition for this. You pick x from the reals. Okay, so we're thinking about them one at a time. So pick an x. Okay? Find a value y in the reals that, I'll put it in quotes, it's not a technical term, but the idea is that works to make this predicate x plus y equals 0 true. Okay? Now, what's your intuition about this statement? Do you think it's true or false?
True.
That's right, Edwin. It is true. And one of the ways that we can discover if a statement is true is to look at some scrap work. Let's try to figure out what the y would be. Like, I usually work scrap work in green. We haven't done a lot of scrap work yet, but in general, it'll be in green. It'll show up better in the scan than it does here under this light. But this is the idea. Let's take an x in the reals, just any x. If it helps you, substitute a numerical value in for x that helps you kind of see, like 5 or whatever your favorite number is. And this is the idea. So here's my little documentation. This is my little symbol that says, hey, the next part doesn't compile, but it's kind of like my thinking notes. We want to find y in the reals to make x plus y equals 0, right? That's what we want to do. So in other words, if we're looking at the equation x plus y equals 0, we want to find the y. So if x was 5, what would be the y that would work?
-5.
Yes. So in general, we can just take this equation and solve for y. So we can see what it looks like. It's going to be in terms of x, like y is related to x. When we find the expression for y, we can just solve for y, just take the x over to the other side. Of course, it's a negative x. And doesn't that make sense? If x is 5, we're going to want to add -5, right? If x was -1/2, what would y need to be? Kendall, what would y need to be if x was -1/2?
+1/2.
+1/2. Everybody seeing it? Kaja, do you see it? Eric, does it make sense? Zane, you with me? Matthew, everybody good? Are we all together? Okay, great. So, sometimes this kind of scrap work is really helpful because when we actually try to write some kind of justification, like, hey, we think it's true. How do we justify it? Well, knowing that what y actually looks like is going to help us write a good justification. So here we go. We're going to say, hey, that's true. Given, here's our justification. Given x in the reals, and it's 1x, but we don't know which one. So we don't, put in a value for x right now because we want it to represent any real number. We just use the variable x. But given x in the reals, just tell your reader, hey, we're going to take y equals -x. Now, there are a couple of things we have to verify. Y has to come from the appropriate domain. So y needs to be real. And it's super simple here. We just say it. X is real, -x is going to be real as well, right? So you can just say, hey, clearly y is in the reals, okay? By saying it, you're simply acknowledging there is a little something to do there. We got to make sure that the y that we select lives in the correct domain, okay? And then, of course, we want to verify that that property holds for our choice of y. So we just say, hey, also, x plus y is equal to x plus -x. And of course, that does equal 0. It's that simple. the scrap work helped us. The scrap work helped us, find an expression for y that makes this algebra work out. Okay? So again, to recap, if it's a for all x there exists, we want to say it for each. We want to think about each x kind of on its own, and for each x, we're looking for a corresponding y. So for each x in D, we find a y in G that makes it the predicate true. Questions? All right, so there's one more kind of quantified statement that has two quantifiers, and that's where the for all and the there exist are switched. Okay, and switching these can matter. Now, I'm just going to give you a little sneak preview in WebAssign. A couple of the questions have to do with this idea that it matters whether the for all comes first or the there exist. And one of the questions gives you a couple of statements that look exactly the same, except that they've switched the quantifiers. So they give you two statements and they're exactly the same, except the quantifiers are switched. And then your job is to figure out, hey, do these have the same truth value? Or is one of them true and the other not? Sometimes they might have the same truth value when you switch the quantifiers. Sometimes switching the quantifiers is enough to make the statements have opposite truth values. It just depends. So we're going to look at an example of that. But first, let's just dig in to this fourth kind of statement with two quantifiers. That's our Roman numeral 4. There exists an x in D such that for all y in G, P of xy is true. Okay. And I'm gonna keep the interpretation up for number 3 so that you can compare. Okay. All right. So how do we interpret this? There exists an x in D such that for all y in G, property P of xy holds. So there exists an x. That means we have got to find one x that will work for every y. See, that was very different than 3. In 3, for each x, we got to poke around and look for a y that would work for that x. Maybe you would find one y that would work for every x, but you didn't have to. Each x could have its own kind of private partner y. And in fact, with this particular example 5, every x has a different y, right? But for there exists an x in D such that for all y in G, P of xy means we must find one value x from set D that works for every y in G to make P of xy true. Very different interpretation. Okay. Now, there might be several x's that you could choose, but you got to just find one that works. Okay. There might be 18 that work. There might be an infinite number of x's that will work for all y. But the point is, we've got to find one and pick that and show it works for all y. There may only be one, and we have to find that one. Okay. I hope I haven't confused you. Let's look at an example. We're going to look at a couple of examples. I'm going to keep this example here. Here we go. There exists an x in the reals such that for all y in the reals, so here D and G are the same set again, x plus y is equal to y. So we need to find a single value x that's going to work no matter what y we pick from the reals to make this equation true. Got any ideas?
Zero.
Yep. That's right. Thank you. That was Eric, right?
Yeah.
Thanks, Eric. Yeah, zero. And in fact, zero's got a special name because it has this property. It's called the additive identity. Because it's kind of interesting. If x is zero, 0 plus y is y. Zero kind of IDs y. You add 0 to y and you get y back. It's like y's looking in a mirror. It's called the additive identity. By the way, there's also a multiplicative identity. If you understand that the additive identity is the number that you can add to y and always get y back, what do you think the multiplicative identity is? It'll serve the same kind of purpose, but not for adding, but for multiplying.
One?
Yeah, 1 is the multiplicative identity. It IDs y. 1 times y equals y, okay? So we have an additive identity and a multiplicative identity in our number system. And in fact, those turn out to be really important objects to have in a number system. All right, so here we go. This is true. Let's see if we can write up why it's true. We've figured out 0 is going to work. So you just tell your reader, hey, let x equal 0. Or you could say choose x equals 0. So we got two things to verify. We've got to make sure we picked a real number for x. Well, you can just say it, clearly, or notice. I like notice. 0 is in the reals, okay? And of course, the second thing to do is to verify that this equation holds. When we use x equals 0, that's super simple. Just, plug in 0 for x. 0 plus y equals y is true for any y in R. And that's it. You kind of sort it out, you figure out what x works, then you present it, verify that x lives in the right domain, and verify that the property holds. Questions? All right, let's do another example of one of these there exists for all. There exists an x in the reals such that for all y in the reals, x plus y equals 0. Now, there's a reason why we're looking at this example, because check it out. It looked a lot like example 5. The only difference is we have changed the order of the quantifiers, right? Example 5 was true. That statement was true. What do you think about the statement in example 7? Can we find a one value x that will work for every y in the reals to make x plus y equals 0 true?
No.
Nope. And it's kind of related to what we were thinking about here for all there exists. Like for each x, like x equals 5, y would be -5. For x equals 3, y would have to be -3. For x equals -0.5, y would have to be +1/2. Different x's have different y's that make x plus y equals 0 true. Okay, these are called additive inverses of each other. There is no single x that can work. So this is going to be a segue into our next topic. When we're disproving a statement, what we're really doing is proving that its negation is true. Now remember, every statement has the opposite truth value from its negation. That's the definition of the negation. It is the statement having the opposite truth value, involving the same variables and domains and whatnot. So when we get ready to argue that this is false, what we actually are going to be doing is arguing that the negation is true. So it turns out sometimes if we are looking at the statement and we can't figure out whether it's true or false, it can be helpful to look at the negation of the statement, and then we can figure out maybe whether that's true or false. Maybe it'll be easier to sort out the negation. Sometimes it is. And once we've figured out whether the negation is true or false, then we know the truth value of the original, because it'll be the opposite of whatever the truth value of the negation is. So that's why being able to negate these statements turns out to be really important, because it can help us as we analyze the truth value. So let's go ahead and write up why this particular statement is false. It's going to get a little wordy, so bear with me. So it is false. So somehow we have to explain that no one single x could possibly work. In other words, for every x in the reals, there's going to be some y in the reals for which x plus y is not equal to 0. That's actually kind of what we're going to argue here. So if such an x in R existed, let's think about what that would mean. It would have to work, I keep putting work in quotes, for every real number y, right? Period. So if it has to work for every real number y, we can look at a couple of real numbers y and show, hey, there's no x that could work for both of those. So there sure cannot be an x that works for every y, because it won't even work for those two. So it would have to work for y equals 5. I guess I got 5 on the brain today. And for y equals 3. Now you could use different values, but just pick 2 different y's. And you can argue that the same x cannot possibly work for both. I'll do it for 5 and 3. We just say, hey, but the x that makes x plus 5 equals 0 true is x equal -5, while the x that makes x plus 3 equals 0 true, or that makes x plus 3 equals 0, is x equals -3. No single x could work for all y, because we can't even find an x that works for these 2 y's. So you just kind of sum it up. No single x could work for all y in the reals to make x plus y equals 0 true. So it's kind of a mouthful here to try to explain it. And one of the things I'm hoping to motivate you toward is the idea that the negation can help us. Just like from the day 6 lecture on Monday, I was trying to motivate you that symbolic notation can be our friend, because there are so many pitfalls with ordinary English. Like we think we're writing the negation, but we might actually be writing something that is not quite the correct negation if we're using ordinary English, because English breaks every rule that you can possibly have. Every grammar rule in English gets broken, right? So in the same sense, tonight I'm trying to encourage you to think, hey, wouldn't it be helpful if we had another, kind of angle of attack at trying to evaluate the truth of a given statement? And that angle of attack is to look at the negation, because maybe it'll be easier to figure out the truth value of the negation. it will certainly be true in Tarski's world problems. All right, so now let's just go through negating multiply quantified statements. I'm actually not going to write this whole page of notes because it's super natural and super simple. You know, the notes are posted. We're just going to read through this together if you don't mind, because, you know, we can save a little time, but we'll talk them through. All right, let's say we want to negate the for all multiply quantified statement. All right, so let's just imagine we're going to negate for all x and d and for all y and g, p of x, y. So the naive thing to do, of course, is just stick a not in front of the whole statement. All right, anybody can do that. 0 credit for just doing that, because that doesn't show any real understanding, and it certainly doesn't help us get a working negation that we can dig into. So this is the deal. When we distribute the not across the multiply quantified statement, it does just what it did with a single quantifier. The for all will flip to there exist. So this for all x and d, when we negate that, that means there exists an x and d. The for all y and g changes to there exists a y and g. And of course, the predicate then gets negated. Now let's talk about why this negation makes sense. If it's not true for every x and d and for every y and g that this property holds, you know, if it's not true for all of them, doesn't that make sense that it means there is at least one x and d and one element y and g for which the property fails? I mean, that's what it means to say it's not true for all. It means there is an x and there is a y for which that property fails. Okay, so bringing the negation through gives us a lot more information, and it clarifies what the negation really says. All right, so when we negate there exists an x and d and there exists a y and g property p of x, y holds. Now let's just think about what that means. That means we can find at least one x in d and at least one y in g to make this predicate true. So if that's not true, so if we're looking at the negation of that, when we bring the not through the statement, the there exists flips to a for all in both of these, and the predicate gets negated. So if it's not true that there's an x and a y that makes p of x, y true, that means for every x and for every y, property p of x, y fails. That's what it means to say there isn't an x and a y. That means that none of the x's and y's work. In other words, for all x's and all y's, the property fails. So it makes sense logically. It is correct logically. By the way, just to remember, you know, that when we look at the negation, we don't change the domain. When we bring this negation through these statements, the domain D and the domain G do not change. If the original statement is something about dogs, like all dogs are loyal, the negation has to be still talking about dogs. The negation is there is at least one dog that's not loyal. It wouldn't make any sense to try to negate a statement about dogs by talking about cats, right? You stick with the dogs. We're still talking about dogs, right? Okay, so when we negate the for all there exists statement, you bring the negation through, the rule works just like you think it should. For all flips to there exists flips to for all, and of course the predicate gets negated. Let's see if we can think through why this makes sense. 3 says for each x in D, we can find a y in G to make P of x, y true. If that's not true, then there is some x in D such that for every single y in G, this property fails. In other words, there's one of these x's at least for which none of these Y's work. And for all these Y's in G, the property fails. Does that make sense? Does anybody have any questions? Well, in the same spirit, when we negate there exists for all, it flips the quantifiers and negates the predicate. If it's not true that there exists an X and D that works for all Y to make P of X, Y true, that means for every single X that you try, there's going to be some Y in G for which the property fails. Every single X fails to work for some Y. So there is no single X that works for all Y to make that predicate true. See what I mean? Okay. So that's how we negate multiply-quantified statements. All right, so now we're ready to shift gears. We're just about on time here. I'm going to show you the Tarski World worksheet. And here's a little thing for class on Monday. I want you to prep for class by doing part 1, write the negation. And I want you to do this is worksheet 1 on here, and I'm going to want you to write the negation of these, and it'll be great practice, and the negation of these. And then we will workshop on Monday. We will work through checking our negations and then determining the truth value of the original statement for each one of these statements. And you can go ahead and work ahead in that too. But let's first talk about Tarski's world, because it's really important that we understand how Tarski's world works, okay? So I am going to write this next page of works to just of notes, because I think it's worth talking through these next notes. These next notes are just about Tarski's world and how it works. All right, Tarski's world. All right, so the domain is the set of objects that you see in the grid. So the domain is the set of objects in the grid. The grid is not part of the domain. The lines in the grid are not part of the domain, okay? It's the objects, all right? And these objects have attributes. Have you had any database theory? Has anybody had any database theory? Okay, well, when you have an object in a database, there's something called the key attribute. It's an attribute that identifies that object as being different from every other object in the database. You can think of it as your social security number. You're the only person with that social security number. You can think of it as your account number, your BGE account or your Amazon account. Anyway, every object has to have some identifying property that distinguishes it from every other object. And for these objects, they have names. And notice the names of the objects are near the beginning of the alphabet. In fact, in all Tarski's world grids, these objects are going to be arranged in alphabetical order. So if you've got like a bad printout, and you can't tell whether that's a C or an E, well, it's A, B, C, D, E, F. So that's an E. They're always in alphabetical order. So they have names and they're near the beginning of the alphabet, okay? Now, what other attributes do you notice? Do you see anything else that distinguishes some properties that they have?
Their shape.
Yeah, they have a shape and they have a shading. So the objects have, I'm going to write the objects have shape. I'll put that as the third one just to match the notes. They have a shape, and each object has some kind of shading. Now in the book, it's actually in color. But here and on the test that you sit for, it's going to be black and white. So the shades here are white, gray, and black. In the book, it's white, light blue, and dark blue. Okay. So here I'll just put white, gray, and black because that's what we have. And of course, now the point is, Tarski was a logician and he wanted to teach students pure logic, and he learned by study and observation that it's enough to build a world where there are 4 different identifying properties: shape, color, name, and the other one is relative position. Not absolute position in the grid, folks, but relative position. In other words, position of these objects relative to one another. And we're going to talk about that more. He also realized he didn't need to use 5 or 6 different shapes in order to demonstrate everything that is to be demonstrated. He just picked 3 shapes, so every Tarski world has objects that are either triangles, circles, or squares, okay? And we're going to talk more about these attributes, okay? Because there's some notation that goes along with these attributes and the usage. So let's talk more about the attributes. And at the same time, we'll learn some notation, which I'm sure you've already noticed just by looking at the worksheet. So here's 1, 2, 3, 4. So for 1, print bold letters. So you notice the names of these are in print, and they're actually bold-faced. I don't know if you can tell that, but print bold letters near the beginning of the alphabet. Are used to identify each object. By the way, when we need variables, italicized letters at the end of the alphabet are used for variables. Like, X, Y, Z, they're italicized. We use those as variables, okay? So you can distinguish between the use by looking at where in the alphabet the letter is. All right, 2, there are 3 shades. Now we're going to get into some notation. If an object is white, then the way we write it is white X. This is called terse Tarski notation. It's terse. We're minimizing keystrokes. And when we say white X, it's kind of like the function, f of X. This means the object X is white, and then black X would be another thing you would see, or gray X. And in the ebook, by the way, is there anybody who is colorblind here? Is there any, because I have a student in another class that's colorblind. The reason I'm asking is in the ebook, when you see the figure of a Tarski's world in WebAssign, there's a tiny little information circle with the eye in it for information. If you click it, then it gives a full description of all of the objects and their colors and what row they're in and everything. So if you need help, if you have some kind of colorblind, you can use that information button. So it's white, light blue, and dark blue. So those are the colors you'll see in WebAssign, because in the book it's in color, okay? But they serve the same purpose. Gray is light blue, and black is dark blue, and white is white. All right, so now more notation stuff, but it's not going to look weird. It's going to look completely reasonable if you understand what's going on so far here. 3 shapes. So you might see triangle, open parentheses, Y. That simply means Y is a triangle, just like you think, or circle Y. And that's the way we write these concepts, square Y. So these are fairly straightforward. The one that gets interesting, or the ones that get interesting, are the ones that have to do with the attribute of relative position. There are 4 functions or attributes having to do with relative position. So there are 4 relative position functions, and they're of the form P of X, Y, okay? All right, so here they are. Let's start with above x, y. All right. They all kind of work the same way. But the way that we interpret this, the first variable, just stick it out front. Okay. So the x just goes out front. And this means x is above y. And we're going to talk about what it means for x to be above y, because that's another pitfall. There's below xy. And that means just exactly what you think it should mean. It means x is below y. Again, the first variable just comes out front. When you think about, the interpretation, then there are two more. Right of xy and left of xy. And right of xy means x is to the right of y, and x is to the right of y. We have to talk about that to make sure that everybody gets what we mean, because there is a pitfall there. And left of xy means x is to the left of y. And if you're like me, my mother always used to joke, I would get my left and my rights mixed up. Double check those when you work those out. Okay, so let's talk more about these, because there's a pitfall here. So more about relative position. So while we do have this discussion, we're going to be looking at figure 1. So here's figure 1. Let's talk about above xy. Figure 1 is the same on both worksheets. So, but I'll just say on worksheet number 1, but it's the same. It's the same on both of them. Okay. All right. So above xy, what does that mean? Because it doesn't mean necessarily what you think it means. Above xy is true if x is in a row that is above the row where y sits. So it's about the rows. It's not about them being lined up in the same column. Object A is above C, but it's also above D, E, F, E, H, F, G, H, I, J, and K. See what I'm saying? A doesn't have to be in the same column of the object as the object to be above it. It simply has to be in a row that's above the row of the object. So A is above every object in here except A and B. So let's look at some true statements. That's the way we're going to practice this, to make sure you understand the idea of above xy, using this figure to look at. So again, we're continuing with above xy. All right, so for example, above AH is true because A is above object H, okay? Of course, above AC is true. A is above C. So, and somebody want to give me another true one that uses two different objects that aren't in the same column, just to make the point? Can you give me another above that's true, but pick me two objects that aren't in the same column, just to make this point that they don't have to be in the same column? No? Okay, so DK. D is above K. Right? but above AB is false. A is not above B. Okay, so that's the idea. Any questions? See, that's the pitfall. People will think they have to be in the same column, but they don't. All right, same idea with below XY, folks. They don't have to be in the same column. So below XY is true if X is in a row below the row in which Y sits or resides, whatever. Okay. So for example, below CA is true. Okay, but that's not really making the point. Below HC is true. You know, H and C aren't in the same column, but H is still below C. Here's a statement that's false. Below GK is false. And again, if you don't see, this is G here. This is D here. Because they're in alphabetical order. G is not below K, okay? So it's the same kind of idea when you start thinking about right of and left of. They don't have to be in the same row to be right of or left of one another. We simply look at the columns they're in. It's a function of what column the objects are in. So right of XY is true if X is in a column that is to the right of the column in which Y sits. So it's about the columns, okay? So, you know, a few true statements, just to get the drift here. Right of EA is true. E is to the right of A because it's in a column that is to the right of the column that A sits in. Right of ED is also true. I mean, they could be in the same row. They just don't have to be. Whereas right of FE is false. Object F is not to the right of object E. In fact, object F is not to the right of any object. It's to the left of most objects, but it's not to the right or the left of itself or D. All right, so that's another thing that's going to happen is if something is true for all, it also has to be true for the object itself. If you're already looking at an object, X, and it has to be true for all Y, Y and X could be the same. You have to check it, make sure it's also true for X. All right, we'll see that happen. And I'm not going to go through left of. I'll let you do that later, just as an exercise. You know, is true if, and you go ahead and finish that. You should be able to finish that statement, and you give examples of some true and false left of statements. You know, take a few minutes after class, you know, and practice with this just to make sure that you can so give some examples of left of statements that are true. Give some that are false. There is one more thing we have to say in order to really thoroughly discuss the relative position. Because This relative position thing is a relation between two objects. When we negate one of these other attribute statements like gray X, well, to negate it, you simply say not gray X, right? Either the object is gray or it's not. It's super simple. But the relative position statements are a little more interesting. Think about this. There's a relative position of the real numbers on the real number line. X could be less than Y. But the negation of X is less than Y isn't that X is greater than Y. It's that X is greater than or equal to Y. See what I mean? So we have to take into consideration what happens when we try to negate above, below, right of, and left of. There's really something going on with that. So let's talk about that. So here's a big fat caution about negating. Because you're going to be doing this when you work on your prep for day 8. You're going to be negating those statements in worksheet 1. And when you are negating relative position statements, we got to be careful. So let me just show you that. All right, let's start with not above. All right, let's say we're going to negate above X, Y. And the way we read this is we can read it not above X, Y. You might think, okay, if it's not above X, Y, then that means it's that below X, Y is true. You might think, hey, the negation of X is above Y would be X is below Y. But that's not the case. This is not logically equivalent to below XY. That's putting that in red. It's not the same thing as below XY. Why not? You see, if they were logically equivalent, if they were, they would always have to have the same truth value. We've learned that much about logical equivalence, right? Logically equivalent statements always have the same truth value. Check it out. Let's look at our diagram here. Again, this is Tarski worksheet 1. Figure 1. Not above A, B is true. You agree? A is not above B. Right? So this statement's true. Not above AB. They're on the same row. But below AB is false. If not above AB meant the same thing as below AB, then these would have to have the same truth value. But you see, the reason they don't is because this is the case like X is equal to Y. They're in the same row together. Neither is above or below the other. So that's why we cannot say that not above AB or not above XY is equal to below XY. It's not. So listen, the upshot here is just use not above XY. That's the takeaway here. Don't try to change not above XY to below XY. They are not logically equivalent. And the reason, of course, here is that X and Y could be in the same row. In which case, above XY is false, and so is below XY. They're both false. They can't be negations of each other. All right. And so this idea of, hey, We can't say that not above is the same thing as below. We gotta think about that for all the other relational position operator. So here's the last page of notes. Let's just walk through it. Not below XY is not the same thing as above XY. Same reasoning. Just use not below XY. Okay. You can find an example where they have opposite truth values. If you pick a couple of objects in the same row, same example would you know, A and B or H and I or J and K in that figure would work out. So not right of XY is not logically equivalent to left of. For example, not right of HK is true because H is not to the right of K. Right? They're in the same column. H is not to the right of K, but left of HK is false because see, H isn't left of or right of K because they're in the same column. See what I'm saying? So just use not right of. Don't try to switch it to left of. Okay. Okay. And then of course, not left of XY doesn't mean the same thing as right of for the very same reason as everything else that I've said, you know, just use not left of. That's the takeaway. All right, so that will help you get the correct negations when you prep. Now, this isn't to turn in, but it's to bring to class on Monday, right? So take the weekend to go through this and do as much, you know, go ahead, you'll have time. There's no excuse. Like for the folks that have Tuesday, Thursday class, we had this lecture yesterday and it sucks to be them because they got to have this done by tomorrow, right? But you've got the whole weekend. Like remember De Morgan's laws, watch these up, and I tried to prep you for this. Like I really have been teaching this class a long time. So special homework 2, folks lost points because you didn't follow the directions. Don't just put the not in front, bring the negation completely through using everything you know about negating statements. That means using De Morgan's laws for negating ands and ors. By the way, if you have triangle T and circle T and gray T, then De Morgan's laws extends and it would be not triangle T. Or the or would change to and. Did I say and before? Hey, wait a second. Hang on. Wait a minute. Hang on. What is this? Let me see. Let's look at this one. There exists a T such that triangle T or circle T. Ooh, that's in parentheses together. And I got these. And gray T. So it's nested. These two go together. And then this one, I'll do this one in red. If you're red green colorblind, I apologize. I'll just make this one bigger. So we're looking for a T that exists so that it's either a triangle or a circle. And once you know, and it's gray. So because there's both an or and an and, we have to be careful when we negate this, folks. It's going to be several step process. The there exists will flip to a for all T. Then we're going to be negating an and statement first because this and operator happens last. So you negate the and statement and then that negates each component. Well, this component is compound, so you would bring the not through that. Would you like to see us? Shall we just do that one? Shall we do that one together? Just to prep you, you know, and just do the best you can, right? We're going to go over this, but let me just show you this particular one. Let's do B. So worksheet number 1, problem 1B. So the statement is there exists, and I always write them down. There exists a T such that triangle T or circle T and gray T. All right. So 1, let's write the negation. The first thing that I will do it in steps. The first thing that happens is, of course, there's a not in front of the whole thing. All right, so I'll write that later. All right, so now let's just look at the, oh, well, maybe there exists a T such that triangle T or circle T. I know, we want to take shortcuts, but it's not good to take shortcuts. Okay, so that's that. This is this. And this one is this big one. Okay. So we bring it through. I'm going to change to blue because it's too hard to read. All right. So when we bring the not through the there exists, that flips to a for all. Okay. But then we negate P of T. All right. So we're going to negate triangle T or circle T, quantity, and gray T. Now we got to bring the negation through that. So for all T, okay, now this is an and statement before it's an or statement, right? This and happens last, so we bring it across that first. So it's not triangle T or circle T. We're going to, this and flips to an or, and then the not gets applied to gray T. Now, we're not quite done because this not now needs to get distributed across this or. There's going to be an and, that's going to flip to an and there's going to be an or, so we still do need parentheses. So it's not triangle T and not circle T or not gray T. So that's the process where you carefully bring the negation through, flipping things, flipping quantifiers, using De Morgan's law. When you bring the not through the and, we get an or. Each component gets negated. Ooh, that was a compound component, so we use De Morgan's law again and bring the negation through, flipping this or to an and. So it's a process. So you have to remember rules like, hey, how do we negate an if-then? Right? Every if-then is universally quantified. Even if we don't see the for all, it's there. And so negation of an if-then is not another if-then, is it? It's an and statement. So you'll have to review your rules. None of this stuff changes. Like the YA, that doesn't change in the negation, okay? You don't change anything with the variables, okay? But we do negate using rules for operators. De Morgan's laws. The negation of if P then Q is P and not Q, okay? And the negation of the quantified statements, you know, it flips the quantifiers. All right. So thanks for playing. There is an office hour at 8. We've run over for 5 minutes, but it's kind of good maybe to see one of these done so that you know what to do. And there'll also be an office hour Sunday night. So if you're working on these and you're stumped and you don't really feel like you've got yourself prepared for Monday night's class, come into office hours Sunday night, right? And we will discuss. All right. If you can't make office hours on Sunday, then you can maybe view the video sometime Monday before class. All right. I've had some people ask for appointments. I've been given appointments at other times. Please feel free to, you know, ask for appointments if you need to meet at a different time. So how many folks are in the room right now? Marcus, Kendall, Danny, Nick, Edwin, Matthew, Ronnie, Khadijah, and Zane. Hey, how about How about I just take attendance right now? We call that a pop quiz, and everybody that's here gets a perfect score. How about that? Let's do our first quiz, and it's just an attendance quiz. Everybody will get a perfect score. It'll be 15 out of 15. All right, I've never gotten a heart ever in all my years of online teaching. Thank you. All right, so let me just make sure I got so Marcus Anderson, Kendall Marks, Danny Nonan, Nick Gorino, sorry if I'm butchering your name, Edwin Mina Lopez, Matthew Smith, Ronnie Huggins, Kaja Fatima, and Zane. All right. Was there somebody else that was in the room that split and that I didn't see go? They're gonna be well.
This
maybe-
at 12 here.
What?
This at 12 like a second ago.
And now we're
Yeah.
like 1, 2, 3, 4, 5, 6, 7, 8, 9. I'll go back and I'll look and I'll give credit to people that were here 5 minutes ago. Okay. All right. I can see attendance. All right. Thanks for playing. And keep up the good work. I hope you're learning something. You got WebAssign to work on. And the worksheets. There's not a special homework. The worksheet is like the special homework, except it's not getting graded until later. All right.